In this example, we're going to conduct approximate analysis of an indeterminate truss. We'll start with some fundamental principles that we'll use to predict the sense of the force, that is, whether it's tension or compression in each member. We'll use that as something we compare against when we're all done. We'll then make some simplifying assumptions, and then we'll apply statics to figure out the approximate force in each and every member of the truss. We'll go back, we'll compare against our prediction to make sure we have confidence in our results. It's a two-panel truss with diagonal members that are crossing. That suggests that it's probably an indeterminate truss. All right, here are the steps we're going to follow. As I said, first thing we'll do is predict the sense of force in each of the members. Then we'll calculate whatever reactions we can Sometimes in an indeterminate truss we can't calculate all of them initially. We'll make our simplifying assumption, or if it's going to be more than one assumption we need, we'll make our simplifying assumptions. During that step we'll also figure out how many we need. Once we've done that, we'll be able to use statics to find all the other forces. Now in this case, method of sections would have worked, but since we want the force in every member, method of joints works just as efficiently. When we're all done, we'll compare our results with our prediction from step 1. All right, let's begin. Step 1. We're going to predict the sense of the force in each member. Okay, so if we consider this truss as a solid beam, let's go back to mechanics of materials. We have our solid beam, pin and roller support, 3-point loads on it. How will it deflect? It will reflect downward in the middle. When that happens, we'll get compression at the top and tension at the bottom, which means when we take a look at our truss, we expect compression in the top chords, tension in the bottom chords. All right, now let's take a free body diagram of joint C. Well, joint C is going to have a vertical reaction up, an unknown vertical force from member CD. It's going to have tension in member BC, which means it'll pull left at that point, and it'll have a diagonal force in member CE. All right, So as we look at that, we've got two unknown internal forces. If I look at horizontal or consider horizontal equilibrium, there's only two members going horizontally, BC and CE. Well, if BC is going to the left, CE must go to the right. And that means that my diagonal is in compression. All right, so this diagonal, and it seems fairly reasonable to presume that this one as well will be in compression. Well, what about the vertical force? We've got up from the reaction, down from the diagonal, and this mystery vertical member CD. I don't think we're going to get it from this free body. Let's move on to free body for the joint D. I have my downward applied load, I have the unknown in CD, I have compression in member DE, so it'll push to the right. I have my unknown in the diagonal BD. Okay, again, let's consider horizontal equilibrium. Only two members have horizontal contributions. DE is going to the right, so BD has got to be to the left, which means my diagonal is in tension. And we'll predict that this one will also be in tension. All right, now what about that vertical member? I've got a downward applied load, I've got a downward force in the diagonal. Well, that leaves me no choice. Member CD has got to be up, which means it's in compression. All right, which suggests that this one will also be in compression. Let's look at a free body of joint E. All right. I've got compression coming from member EF, compression coming from member DE. I've got the downward applied load. I have compression coming from the diagonal CE and compression coming from the diagonal AE, and I have this mystery BE. Well, I have some downward force and some upward force. I don't think I can figure this one out from this joint or this free body. Let's try joint B. I've got tension coming from member BA, tension coming from member BC, tension coming from the diagonal BF, and tension coming from the diagonal BD, and we have our mystery BE. Now I can see I've only got vertical or upward force on the joint coming from the diagonals. My mystery BE, the vertical member, must be down, which makes it compression. All right, we have our prediction for each member of the indeterminate truss. Now we need to calculate reactions. All right, step 2. Let's calculate as many of the reactions as we can. Let's see, we have a pin support at A, so I have AX and AY. I have a roller at C, so I only have CY. 3 reactions, 3 unknowns, 3 equations of equilibrium. I do believe we can get all of them from just equilibrium. Let's start with forces in the x direction. Our only contribution is AX, so that one's 0. Great. Now let's sum moments. I'll go clockwise as positive. And let's sum moments about point A. We know those have to add up to 0. I have the 600 pounds through 8 feet, the 300 pounds through 16 feet, and we'll subtract out reaction CY through 16 feet. If I solve for CY, we'll get 600 pounds. It's a positive quantity, which means it's in the direction drawn. It's up. Let's sum vertical forces. We'll call up positive. I have my unknown AY. Have my negative 200 pounds, the downward applied force, and we have 600 pounds downward and 300 pounds downward, and we have our vertical reaction at C, which is 600 pounds back up, which is going to give me AY is a positive 500 pounds. It is also the direction drawn, which is up. So great, I have my reactions. Now we're ready to figure out how many assumptions we need. Step 3. We're going to make our simplifying assumption or multiple assumptions. So let's actually figure out how many we need. That's going to be dictated by how many degrees indeterminate is our truss. Well, let's see. How many elements in the truss? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 elements, one unknown for each element. Reactions. There are 3 reactions. So my total unknowns for the truss are 14. Now, equations of equilibrium. We'll count up the number of joints. 1, 2, 3, 4, 5, 6. With 2 equations of equilibrium per joint for a 2D truss, we get 12. Number of unknowns minus the number of equations gives me my degree indeterminacy. Therefore, since we have 2 degrees indeterminate, we need 2 assumptions. What shall they be? Well, it turns out we're going to make the same assumption, but we're going to do it twice. Each diagonal in a panel contributes equally to the shear in the panel. Since we have 2 panels, we now have 2 assumptions. Let's see how that works and actually calculate the axial force in each diagonal using our assumptions. Cut our truss right through the first panel. And let's draw a free body of just the left part. I'm going to consider it more like a solid beam so I can get the net internal force at the cut. We have our 500-pound vertical reaction, our 200-pound applied load, our unknown shear at the cut, and our unknown moment at the cut. I'll apply vertical equilibrium. Have our 500 pounds up, 200 pounds down, and our unknown shear down. Move shear to the other side, solve, and we'll get 300 pounds in the direction drawn. All right. So what does that mean for us? Well, let's draw that part we kept. We'll consider the members as well. I have an unknown in each member. I know that the geometry of my diagonals is a 3, 4, 5. Now, we said that we're going to take the shear, the net shear at the cut, and we're going to divide it up so that each of these two diagonals carries half. Well, if this diagonal, the top one, BF, carries downward force, it must be in tension. And if diagonal AE carries downward force, it must be in compression. So let's calculate for member BF. Using our geometry, the axial force is going to be 5/3 of the vertical component, which is 150 pounds, which means we'll get 250 pounds. And we said that's tension. So now we'll take our other member, AE. Again, we'll need 5/3 of the vertical contribution will be the net axial, 250 pounds. This one's in compression. Okay, now let's cut it at the other panel and see what we get. This time I'll draw the right piece with our 300-pound applied load, our 600-pound vertical reaction, our unknown shear and moment at the diagonal, or at the cut rather. Let's apply vertical equilibrium. We have the shear up, the 300 pounds down, the 600 pounds up. Solving for the unknown shear at the cut, we're going to get a minus 300 pounds this time. So it is not in the direction we drew it. That's okay. The implication, we can handle that. Let's draw that piece of the structure with our unknown diagonals. We now know that instead of up, the vertical contribution of 150 pounds is down in each one. All right. And so what does that mean for member BD? It means that force in member BD is going to equal, again, 5/3 times 150 pounds. 250 pounds in that diagonal, and this one is in tension. And we look at our other diagonal, force in member CE, and that will be 5/3 times 150 pounds. 250 pounds. This one's in compression. Great, so we've now taken care of or calculated 4 of our internal forces. We've used our assumption to help us out with the indeterminacy, and so we'll use method of joints start calculating reactions for, or not reactions, but internal forces and all the rest of the members. I'm going to start at joint D for our step 4. All right, we have downward applied load, 300 pounds. We have unknown force that I'll assume tension until we calculate otherwise in member CD. We have our diagonal, BD, which we know is 250 pounds in tension. And we'll have our unknown, which I'll assume tension for now, in member DE. All right. We're ready to apply equilibrium. I'll start with forces in the X. We'll assume to the right is positive, and I'll have the negative contribution of the member of DE, and a negative contribution, which will be 4/5 of the total in the diagonal, 250 pounds. And those are the only two elements in that direction. So the force in member DE is negative, and it's 200 pounds. And since I drew it positive, or I drew positive as tension, it means that negative tells me it's a compression member. Okay. Now, forces in the Y. We have the 300 pounds applied load down. We have a contribution from the diagonal, and that's 3/5 of its total. And we have our unknown force in member CD. Put them all together. I'm going to get a negative again. And this is 450 pounds. Or the other way to say it is 450 pounds in compression. Okay. Now let's go joint C. We have our reaction of 600 pounds. We have the force in member CD, which we calculated to be a negative 450 pounds. It's in compression. We have our diagonal, which we calculated to be a negative 250 pounds. It's in compression. We have our unknown in member BC. Since we only have one unknown, we're only going to need one equilibrium. Let's apply horizontal equilibrium. We'll take to the right as positive. I'll have a negative force in the member BC. And I'll have negative the horizontal contribution of the diagonal, which will be 4/5 of its total, which is a negative 250 pounds. Put those together, move BC to the other side, and I'm going to get a positive 200 pounds. Since it's positive, that means it is in tension. All right. Now we're ready to move on to joint F. All right. At joint F, I have my 200 pounds applied downward force. My unknown force in member EF, the top chord. I have my diagonal, which I know is 250 pounds tension. I have my unknown vertical force in member AF. Let's start by applying horizontal equilibrium. I have my unknown in the top chord member, and I have the horizontal contribution of my diagonal member. And so my top chord is going to be a negative quantity. It will be 200 pounds, which means it's actually 200 pounds in compression. Apply vertical equilibrium. We'll take up as positive. I have my unknown force in member AF. I have my 200 pounds applied downward force, and I have the vertical component of my 250-pound diagonal. Move force in member AF to the left side. I'm going to get a negative quantity, and that's going to add up to 350 pounds, which means 350 pounds in compression. Well, at this point, let's stop for a second and see which members have we not solved. We figured out both of the top chords, all of the diagonals, the two outer vertical members, and one of the bottom chords. It's just one bottom chord and one vertical member yet to solve. So from here, let's go to joint B, where there's only two unknowns, so I know with my method of joints I can solve to find the internal forces right there. So at joint B, I know that the bottom chord to the right, member BC, carries 200 pounds tension. I know that each of my diagonals are in tension with 250 pounds. Don't know the force in member BE or AB. So let's start off by applying horizontal equilibrium. Consider to the right as positive. I have my unknown AB, and I have the horizontal contribution back to the left, 4/5 of the 250 pounds tension in the diagonal. And I have the horizontal contribution to the right, the 250 pound diagonal, and the 200 pounds in the bottom chord. Well, this and this cancel out. Bring the force in member AB to the other side, and it's a positive 200 pounds. It is in tension. One left. Some forces in the Y, I'll take up as positive. We get the vertical component of the left diagonal. We get our unknown member BE, and we get the vertical component of the right diagonal. Put those together, move BE to the other side. This one becomes negative, and it's a negative 300 pounds, which means it's 300 pounds compression. Let's summarize what we learned in our analysis in steps 3 and 4. Each of the top chords is 200 pounds compression. Each of the bottom chords, 200 pounds tension. Each of the diagonals, 250 pounds. And the diagonals gathering here at point B were in tension. The diagonals gathering up here at point E were in compression. My vertical members, we had 350 pounds. That's a 50. Compression here at AF. 300 pounds. Compression here in member BE. 450 pounds compression here at member CD. So now we're ready for step 5. Let's go back and compare with our prediction. So carefully take a look at the compression and tension layout. Top chords in compression, bottom chords in tension. All verticals are in compression. The diagonals gathering down at point B are in tension. The diagonals gathering up at point E are in compression. As we take a look back, it's our results of step 1. Top chords in compression, bottom chords in tension, verticals are all in compression. The diagonals gathering down at point B are in tension. The diagonals gathering up at point E are in compression. Matches our prediction exactly. That's a good sign. Not a guarantee that we didn't make a mistake, but a good sign that we've got reasonable results. So let's review what we've done. We started with prediction of the sense of the force in each member. We used some mechanics of materials, deflected shape of a solid beam to get a sense of where will the compression and where will the tension be. Then we used a qualitative method of joints to figure out what direction or what sense each of the remaining forces needed to be. We wrote down those. Then we were ready to calculate reactions. Turns out we had only 3 unknown reactions with 3 equations of equilibrium. We could calculate all of those reactions. Then in step 3, we had to figure out how many degrees indeterminate is our truss. Because with 2 degrees indeterminate, that means we need 2 assumptions. And we actually made the same assumption twice. And our assumption is each diagonal in a panel contributes equally to the net shear in that panel. Well, to apply that, we had to cut the panel, calculate the net shear, and then we distributed half to each of the diagonals. Based on the direction of the net shear, we could figure out the sense of the force in each of the diagonals. We did that for both panels. Then we were ready to apply method of joints to figure out the rest of the internal forces. We started at joint D. There were only 2 unknowns there. And then moved to joint C. Figured out the bottom chord. By jumping all the way across the structure to joint F, we figured out the remaining top chord and the vertical at AF, and it left us with only 2 unknowns, and joint B contained both of those unknowns, so our last joint was B, and we figured out the rest of our truss forces. We summarized those on the picture of the truss. We compared it with our prediction at the beginning, and lo and behold, it compared well. Great job.